One of the ideas that's very prevalent in organic chemistry for deciding what reactions might take place or how they might take place, and whether something is stable or not, is the idea of formal charges. And formal charges are not real charges, but they're a tool we use to help determine the distribution of electron density, and thus the distribution of charges in a molecule or ion. So wherever there's an excess of electrons, you're going to have a negative charge, and wherever there's a deficiency of electrons, you're going to have a positive charge. So this idea of formal charge is an accounting tool. Formal charges are not real charges, but it's an accounting tool to give us some kind of indication of whether there's going to be positive or negative charge accumulating on a particular atom in the molecule. And if you have an atom that's gaining a bunch of formal charge, like a negative formal charge would then cause it to attract a cation or a proton. So this is really an important idea for trying to decide how reactions will take place and whether things are stable or not. So what we're going to do is compare the number of valence electrons in a neutral atom to the number of valence electrons that we would assign to the atom as it's bonded in the Lewis structure. If the atom has more electrons assigned to it in the Lewis structure than in the neutral atom, then it's got extra electrons and would get a formal negative charge. A formal negative charge. And if I just look at a potential bonding scheme for an atom that obeys the octet rule, so let's say we had an oxygen that was triple bonded to something, then it would need a lone pair to complete its octet. Right? And so a neutral oxygen would have 6 valence electrons. And the question is, how many electrons would this oxygen own? How many would be assigned to it as it's bonded to some other atom with a triple bond? And so the key idea here is the idea of sharing. So let me see, we got to review sharing a little bit, and I like demonstrating this with a volunteer from the audience in a regular lecture, because sharing is an idea that we all sort of understand, although people that are really greedy don't really understand sharing. So right here we have a line that indicates a bond between atoms X and Y. And I'm going to go ahead and draw some other bonding that's going on here. So we'll double bond X to an oxygen, and then we'll fill the octets of all the atoms so they're now obeying the octet rule, right? Now the shared pair of electrons, if you're to ask from the shared pair, so there's 2 electrons here associated by the line, who owns those 2 electrons? If you understand sharing real well, then you'd understand that if these atoms were split up and divide things equally, each atom would get 1 of the shared electrons. So if you got a shared pair of electrons, 1 electron is assigned to each atom. So if you have something that's got 3 lone pairs and 1 bonding pair in its environment, it would get the lone pairs all to itself, 1, 2, 3, 4, 5, 6 electrons all to itself, plus it gets 1 from the shared pair. So this mysterious Y atom would have 7 valence electrons assigned to it. So we just distribute the electrons so that anything that's unshared, it owns all by itself, and then for each shared pair of electrons, for each bond that the atom has to it, it would get 1 of the electrons from the bond. So this Y is very electron rich in some sense, because it's got 6 electrons all to itself plus 1 from the shared pair is 7. This X, on the other hand, has 2 electrons all to itself, plus it gets 1 electron from each of the shared pairs. So 1, 2, 3, 4, 5 valence electrons assigned to the X atom. And then for the oxygen here, it's in between those two. The oxygen has 1, 2, 3, 4 electrons that it owns all to itself, plus it gets 1 from each of the shared pairs, and so you have 6 valence electrons assigned to it. Or the way I like to think of it is it owns 6 of those valence electrons in the bond, in the molecule or ion. Alright, so that's how we figure out how many electrons are assigned to each atom as it's bonded in the structure. So let's go back to where I was going to do some examples of atoms with formal charges. You can have an oxygen that's triple bonded with 1 lone pair, and then it would obey the octet rule. We could have an oxygen that's got 2 bonds and 2 lone pairs, and then it obeys the octet rule. Or we can have an oxygen that's got 3 bonds to it and 1 lone pair, and it would obey the octet rule. And these are some of the patterns that you'll see for oxygen as it's bonded in molecules. And remember, the neutral oxygen has 6 valence electrons, and that's our sort of base for this understanding, or our starting point, that if an oxygen has 6 valence electrons, it's neutral and has no charge. Now, when an oxygen is triple bonded with a lone pair, like in carbon monoxide, then we assign 1, 2, 3, 4, 5 electrons to it. So this has 5 valence electrons in this structure, whatever it is. So that's 1 less, so that makes an oxygen, when it's triple bonded to some other element and obeying the octet rule, have a positive 1 formal charge, because in this structure it has 1 fewer electron than it would be if it were a neutral oxygen. If you have an oxygen that's got 2 bonds to it and 2 lone pairs, again, how do you assign the electrons to it? 1, 2, 3, 4 all to itself, plus 1, 2 from the shared pairs, 6 valence electrons. So this one, and we wouldn't usually write the 0 formal charge, but when I'm teaching something I like to be super complete. So the neutral oxygen has 6 valence electrons. There are 6 valence electrons on the oxygen in this structure, or as it's bonded in this way, so that's a 0 formal charge. And now if you have oxygen with 3 bonds and a lone pair, again, 1, 2, 3, 4, 5, this is just like a triple bond and a lone pair. So you get 5 valence electrons in this structure, so this oxygen is formally positive as well. So you might be wondering now, how does an oxygen get a negative formal charge? And that's actually very, very, very common in inorganic and organic molecules, because oxygen is pretty good at pulling electrons to itself. It's more likely, or very likely, to have 3 lone pairs and 1 bond to complete its octet rule. And now if you count the number of electrons that we assign to it in the structure, then you have 1, 2, 3, 4, 5, 6, 7 electrons assigned to the oxygen. That's 1 more than it would have if it's neutral, so it's a single bonded oxygen has a negative 1 formal charge in the structure in which it's singly bonded like that if it's obeying the octet rule. So 7 valence electrons in this structure. And it's sort of a partial structure because I'm not showing a whole molecule, I'm just showing the little piece of it and how the oxygen is bonded to the rest of the molecule. And that's all you need to look at to assign formal charges. So this is, again, an overview of how to determine formal charges. It's always a lot more understandable for me if I show some concrete examples. So let's look at a few things here. We looked at the dot structure for nitrite in a previous video, and this one involved resonance forms, right? So the static structure like this indicates that one bond is shorter, one bond's longer. That's not the way it is in real life. So we alternate or draw the two different individual pictures, which averaged collectively is a better representation of the molecule. So if the left structure, the left bond is longer, in the right structure the right bond is longer, in the average of the two structures the bond lengths are equal. So that's something, if you haven't seen the resonance video or the how to draw Lewis structures video, look at those to make sure you understand resonance. But if you're just looking for formal charge, again, you're going to compare the number of valence electrons that the neutral atom has. So I put a little note here that oxygen has 6 valence electrons, nitrogen has 5, and oxygen has 6. Right, so that would be the neutral atoms would have that many valence electrons. Then I'm going to assign the number of electrons it has in the structure. So this left oxygen has 1, 2, 3, 4, 5, 6 all to itself, plus 1 is 7. So that is an extra electron. Number of electron assigned to it is 7, so that makes it a minus. And you'll see that repeatedly through inorganic and organic structures alike. A singly bonded oxygen that's obeying the octet rule gets a minus formal charge, and you can see hopefully how I made that assignment. The nitrogen in the center, if it were neutral, it'd have 5 valence electrons. Let's see what we assign to it. 1, 2, 3, 4, 5. Again, all the lone electrons it owns entirely, so I count 1 for each of those. And then for each shared pair of electrons, it gets one of the two. So 1, 2, 3, 4, 5. This nitrogen in the center has no formal charge. We normally wouldn't write it, but again, want to emphasize what the formal charge is here, and that we've determined all of them. And then the right oxygen, we assign it 1, 2, 3, 4, 5, 6 electrons, which is the same as the neutral atom, so again, that's formally 0. One of the things that's really important about formal charges is the sum of the formal charges for each atom in a molecule or ion must add to, or the sum of the formal charges is equal to the overall charge on the molecule or ion. So you notice overall we have a negative charge. We're essentially describing where is that negative charge likely to reside. It's going to be on the singly bonded oxygen. And if you look at the right structure, it's very similar. The double bonded oxygen, 0 formal charge. The nitrogen in the center, 0 formal charge. The singly bonded oxygen, minus 1. And one of the things that this tells us when we take resonance into account is that each oxygen is negative half the time. So a better picture of this, or a different picture that a lot of people like, they call the resonance hybrid, where we're trying to draw the bonds as being between single and double bonds, right? And then in terms of formal charge, the negative charge that exists in the ion is spread between the two oxygens. So it's like each one has a 1/2 formal charge. Now I've always disliked this resonance hybrid kind of look to things, because with the dashed lines and the spreading out of electron pairs, I can't count how many electrons are there very easily. So even if I filled these in so they were more like they had octets, I don't know how many total electrons are there. I get an idea that the nitrogen-oxygen bonds are the same, and that the negative charge is split evenly between the two oxygens. So in that sense, this type of drawing is useful, but I like the traditional Lewis structure a little more. So that's nitrite, which is one of the examples. Another one that we had looked at when we talked about resonance is carbonate. And I'm just going to draw the one static structure for carbonate and not all the resonance forms. Carbonate has an overall -2 charge. And right off the bat, hopefully, if you've done enough work with oxygens and their formal charges, you can see we have a singly bonded oxygen, that would be -1. We have a singly bonded oxygen, that would be -1. And then over here we have a doubly bonded oxygen, so we would give that a neutral formal charge, 0. Again, how do we get that? If an oxygen was neutral, it'd have 6 valence electrons. This one we assign 1, 2, 3, 4, 5, 6, 7. So that's why it's got an extra electron and is -1. So in carbonate, the formal charges are the singly bonded oxygens get -1, the doubly bonded oxygen and the carbon have formal charge 0. Again, I know the sum of the formal charges has to equal -2, so I sort of knew before I even determined it that this carbon had to be 0 because the -2 had already been taken care of by the oxygens. But let's verify. Carbon would have 4 valence electrons if it's neutral. We assign 1 for each bond. And we get 4 electrons assigned to the carbon, which is what it would have if it were neutral. And another good thing that formal charge is used for is determining the relative stability of different resonance forms that you might draw. And we try to minimize formal charges in resonance forms and try to come up with a better Lewis dot structure by rearranging the electrons to minimize the formal charges if we could. So that's something I think we'll address in a future video, is if we have different resonance forms, how do we pick the one that we like the most? And one of the things that is a standard rule in chemistry is we want the formal charges to be minimized if possible. So hopefully this is helpful, showing how to determine the formal charge for different atoms in a molecule or ion. And we'll do some more examples in a future video.